Okay, so this is the replacement lecture for, this is lecture 11, but I believe this is lecture 12, so this is kind of confusing. So this is the replacement lecture for the one that was eaten by YouTube. It turns out it was entirely a YouTube problem because other instructors at other universities that I know that also stream on YouTube had the exact same issue at the same time, so was definitely a YouTube issue, so hopefully that won't be affecting us too many more times. It's literally the second time that's happened in like 100-ish lectures. So anyway, so I'm just going to redo this entire first bit. So going through this again, um, the idea is that the second we have coordinates, uh, we wish to introduce algebra using these coordinates in, you could say, an obvious or straightforward way, which is to define operations of addition and a type of multiplication, both of which have some geometric meanings attached to them, or are geometrically convenient to talk about, and mimic these familiar properties coming from sums of real numbers. So here are the list of properties. So what is the idea here? Rather than treat these as just the coordinate points before, I'm renaming them vectors. Of course, you all have seen vectors before. You're familiar with vectors as an object, and so I'll be calling them vectors and points interchangeably, but what a vector is for us at this point is just, or at least a vector in R2 in the plane, is just an ordered pair. As we'll see, the benefit, of course, of switching to this is that it's very easy to move to higher dimensional settings using this same language. So a vector is a vector is a vector in the plane is an ordered pair. So u and v are represented by points here in the plane. And so our notion of vector sum is the usual one. It is component-wise. So to sum the vectors, or the ordered pairs u and v, I just sum them in each ordered pair slot. Right? So I sum them in each component. That is my vector sum. So geometrically, why we might be interested in that is, of course, the parallelogram rule for vector sum, which is if I have two vectors, u and v, represented by these 2 points in the plane, the vector sum u plus v is the fourth vertex in the parallelogram that has the other three vertices, 0, u, and v. This 0 is the origin, of course. I'm using this zero vector notation, so I'll talk about that again in a second. And so that's our notion of vector addition. It's the usual one, and geometrically, this is determined as this missing fourth vertex in the following parallelogram, this one here. Okay, so similarly, scalar multiplication is defined in the usual way. So a scalar is just a real number. Multiplying by a vector or an ordered pair by a scalar is just multiplying each of the components by that scalar. And so what does this do geometrically? So let me zoom in here. So geometrically, this is a scaling, right? And that's why we call them scalars. So if I have three vectors or three ordered pairs, u, v, and w, that determine a triangle here, and then I plot in my same plane AU, AV, and AW, where here this particular choice of my scalar A is 2.5, then what results is that I have a similar triangle here that is just a scaled up version of the triangle I began with. So the scale factor here is 2.5. Okay. And so that is the geometric meaning behind the scalar multiplication. Okay. And now it turns out, of course, that for vectors in R2 defined in this way, these two operations satisfy the following list of 8 axioms. So one is, it doesn't matter what order I do the vector space addition. Note that this is inherited from the fact that the reals satisfy this. So in each slot I have this sum. So reversing u plus v, making that v plus u, I'm reversing the order of addition in each slot. But since addition is commutative in the reals, it's commutative in each slot, and so vector sum is commutative. That's how a lot of these are going to go. In fact, all of these properties are inherited from the corresponding properties from the reals. Okay, and so I've called these the vector space axioms. We'll see why in just a second. But note the first four deal solely with the plus operation. So this number 2 is just saying that vector sums are associative. Right, so it doesn't, notice the UVW ordering doesn't change here. It's just the parentheses. Here, this is saying that there is a zero vector here that satisfies or is the zero object for this operation plus. That is, for any vector u, when I add the zero vector to it, I just get u. And also, there exists some thing in symbol, right, called minus u, that is the additive inverse for a vector u. And so this additive inverse, when added to any vector, produces a zero vector. Okay, and then similarly we have these nice properties, scalar multiplication. So if I use the unit from the reals, so 1, and I scalar multiply vector by 1, I just get the same vector. And then I have distributive properties in both slots, so in the vector sum slot and in the scalar slot. So I can sum in the scalars, and that's also distributive. And then lastly, this scalar multiplication is associative. I can actually do the scalar multiplication first if I have a couple of them in sequence. Okay, and so these are familiar things. These are called the vector space axioms. Okay, so the reason for that is the following. I can define a real vector space to be a set V of objects. We'll call them vectors. The reason for being so vague here, of course, is, as you may have seen before, when we say vectors, these things might not be the traditional things you think of as vectors, that is like an ordered pair rising immediately from, like, say, some point in the plane or a point in 3 space. But you can also define a vector space of, say, functions. So the vector space of continuous functions defined on some closed interval. That, for instance, is a vector space where the operations in question, so vector sum in that case, is not the sum of the slots. It is pointwise sum of functions, for instance. Okay, so we can talk about vector spaces even in that sort of generality. We're not going to do that typically, so but that's the need. That's why we're being so general, so that we're also covering those kind of bases. So a real vector space is a set of objects we'll call vectors that has 2 operations, a plus and a scalar multiplication. Okay, and so there are a couple of properties that this thing satisfies. So one, it is closed with respect to both vector sum and scalar multiplication. So whenever I have 2 objects of V and I perform one of these operations, the resulting object is necessarily in V. That's all that one says here. 2, there exists a zero vector that is this zero object, satisfies that zero object axiom in our previous list. And each vector has an additive inverse minus u. So each vector u has an additive inverse in symbols minus u that satisfies this axiom that when you add it to its additive inverse, you get this zero vector thing. Of course, it turns out that this minus u is not just a convenient symbol. It is exactly what you think it is. It's the same thing as minus 1 scalar multiplied by the vector u. Okay, and V satisfies that previous list of vector space axioms. So bringing it back real quick, there's the list. So V is space that is closed under scalar multiplication. There's a zero vector in V. So this is saying, without explicitly saying it, this is saying that V can't be empty, right? V has to at least have the zero vector. Okay. So there's a zero vector in V, and then all the other vectors have additive inverses. Of course, a zero vector is its own additive inverse, and so on. And V satisfies that list of vector space axioms. Okay. Now, this tells us immediately that R2 is a vector space. I say, or R2 is a vector here. R2 is a vector space. Sometimes I will abbreviate vector space, as you probably saw in 240 or 461, as VS. So R2 is a vector space because it satisfies that list of things. It satisfies the vector space axioms and 1 and 2 as well. So these operations are closed. There's a zero vectors. There's an additive inverse for every vector. Okay. Similarly, R3 is also a vector space, right? By the same, by virtue of the same fact, if you now define vectors U and V to be ordered triples, right? So points in space, define analogously vector sum and scalar multiplication. What do you get? Well, you get that R3 is also a vector space. And so any sort of analysis that we were going to do in R2, we can do a similar sort of study of R3. And in fact, we can keep going here, right? So you're familiar with how this works. If I wanted to do R4, that's ordered quadruples, right? Ordered 4 tuples. Then I could define them similarly. And what's nice is that we are going to develop geometry using this. And there's nothing special about one over the other in terms of dealing with it as a vector space. Adding an additional slot here algebraically is not that big of a deal. But trying to do this the Euclidean way is a real nightmare, right? And so, to show you what happens when you're looking at like the end stuff that Euclid is doing at the very end of the elements, here, I think in book 12 there's plenty of these that are pretty rough. I mean, that's a nice picture. These aren't so bad. So let me find some of the real bad stuff. I mean, these start to be a little iffy. Here's some diagrams that are a little iffy as well. See here's some stuff. Here's some diagrams that are a real headache to sort through. And what is nice is that we can avoid entirely dealing with diagrams of this sort by abusing the fact that we can describe R3 very simply, right, as a vector space. Okay, and so the importance here is that all we need algebraically in order to actually prove all of those theorems of Euclid in this setting, even in the setting of R3, so the three-dimensional Euclidean geometry, all we need is the notion of length, which arises from the inner product or the dot product. Once we have that, we have all the tools already just from this algebra to set up and prove all of the Euclidean geometry facts using this approach. Okay, so that's the strength of using this setting. Okay, now more geometric groundwork. Okay, the notion of direction and linear independence. Okay, so the first way in which you were introduced to vectors, you may have been told that a vector is an arrow, right? And so by that, what was meant was a vector is a direction, right? So the direction the arrow is pointing, and a length, right? The length of the associated line segment that the vector was represented by. And so we'll get to the length bit in a second. Right now, a vector for us is just a point. It's just an ordered pair, say, in R2. So then where does the direction in R2 come from? Well, we take that point, and then the direction associated to it is just the direction indicated by the line that passes through the origin and that point. Right, so any point in the plane, there's a single unique line determined by that point in the origin. So the line passing through the origin and that point. So if u is any non-zero vector, then multiples, that is all these scalar multiples au of u, make up the line through 0 and u. Okay, and we call those points or that collection of points, the points in the direction of u from 0. Now, there's a little thing here. You might ask, wait, like that's the full line, right? Isn't minus u, for instance, or minus 5u in the opposite direction of u from 0? The answer to that is we could certainly distinguish between those if we wanted to. So we could deal with half lines instead. We could say, there's line from 0 to u, and that is the half line, right, from the origin to that point. And then there's the other direction, which is 0 to minus u, which is the other half line. But really, there's not that much of a reason to distinguish between those things. And so we just call them all the same direction, even if, in normal English terms, you would understand that they're in opposite directions. The point is they lie on the same line, okay? And so that's what we mean by direction here. Okay, and so the non-zero vectors u and v have different directions from 0 if neither is a multiple of each other. Okay, and you might immediately notice that this has some implications coming from and going to linear algebra in terms of linear independence. Okay, and so if you have a set of two vectors that are linearly independent, if and only if they're not scalar multiples of each other. Okay, and so defining them in this way, geometrically, we can define what it means for u and v to have different directions from 0, because neither's a multiple of each other. But that way, because the line from 0 to those vectors is the set of all scalar multiples, right, of those vectors. So if they're not scalar multiples of each other, they don't lie on those lines. Right, so neither of them lies on the other line, so neither is a multiple of each other, thus they're linearly independent. That is, there are no real numbers a and b that are not both 0, such that au plus bv is the 0 vector. Okay, and so this gives us a nice generalization in general, which is to say that a vector w has direction u, which is also a vector, from v, another vector, or relative to v, if w minus v is a multiple of u. Okay, so we also say, an equivalent way of saying this is w minus v has direction u. Okay, so w minus v has direction u is another thing that we'll say here. So the question is, what is going on here? It might help to actually draw some pictures here in a second. So another thing that follows immediately from this, we call two vectors parallel if they have the same direction. Okay, so two vectors are parallel if they have the same direction, i.e., what does that mean? Oh, I'm a little bit off the page here. So two vectors are parallel if they have the same direction, i.e., w minus v is equal to a times t minus s for some scalar a, which is a real number. What does this mean? This occurs if and only if the line segments from v to w and s to t are parallel. So this is a formulation of two line segments being parallel. Okay. All right. So note, we may view w minus v as an abbreviation for the line segment from v to w. That is, from the point determined by v to the point determined by w. Think geometrically about why that is, right? Knowing what you know about vector sum, think about why you can treat vector subtraction in this way. Of course, you've seen this plenty of times before, but this is still a nice thing to think about to really nail down what's going on here at the foundational level. Okay, So what are some pictures that kind of show what's happening here? Well, let's say that we have a line segment, so that is 0 vector to u. Okay, and we have another line segment that goes from v to w. This w is v plus 3/2 u. Okay, and another line segment that is s to t, and t is s plus 1/2 u. Okay, so these are parallel line segments with direction u. Okay, note that w minus v is 3/2 u, that is, it's a multiple of u, and t minus s is 1/2 u. Thus, w minus v is equal to 3 times t minus s. Okay, and so in this same notion, in this same exact way, we have this satisfied that, so what did this condition tell us? It told us that the line segments from v to w from s to t are parallel. So these two line segments are parallel, and they're parallel because of this relation that they have. Okay, these two relations tell me that they're parallel to u. Okay, but these two, or this relation here, tells me that they're parallel to each other. Okay, without even having to involve u at all. Okay. All right, so that's how that goes. Now, to show kind of where we're going with this, the idea is to do the following. So now we wish to use this setting to prove analogs of the Thales theorem and Pappus theorem. Okay, so there is the vector Thales theorem. What is the vector Thales theorem? Okay, so if S and V are on one line through 0 and this makes it seem a little strange here, so I'll explain. If S and V are on one line through 0, and T, maybe what I should do here is rather than use the word and, I'm going to use the symbol and to denote that that's it, I'm done here. Okay, and T and W are on another line through 0. And maybe I should use my symbol again. There we go. And W minus V is parallel to T minus S. That is to say, the line segment from V to W is parallel to the line segment from S to T. Then V is equal to AS and W is equal to AT for some number A. Okay, so first question you might have is, what does this have to do? How is this the Thales theorem that we saw previously in Chapter 2? That's actually going to be the subject of a homework question that I'm going to assign for you all in your next homework set. So so that will come up then. Okay. So, and that will, if you have questions about that, you can ask me in office hours. But that's basically, I'm going to give you all a problem that asks you to draw the picture here. I'm specifically not going to draw the picture. I'm going to do the proof without the picture. But then what I want you to do in this problem is to draw the picture and explain why this statement is the Thales theorem. Okay, note what this has to do with segments being proportional. Okay, so let's prove this. If W minus V is parallel to T minus S, then by definition, what does that mean? Well, we just saw what that means on the previous page. What that means is that they're scalar multiples of each other, right? There's some A that is some real number such that these things are scalar multiples. That's what it means if those are parallel. Then W minus V is equal to A times T minus S. But using vector space axioms, this means that this is AT minus AS. That is, for some A, it's a real number. Okay. Now, because S and V are on the same line through 0, so because S and V are on the same line through 0, V is equal to BS for some B and R. They're scalar multiples, right? That's what it means to lie on the same line, right? The line through 0 containing a vector is defined to be all the collection of all scalar multiples of that vector. Of course, this is assuming the vectors are non-zero, right? We're not in a degenerate case here. Okay, similarly, W is equal to CT for some real number C. The reason for that being that W and T lie on some other line through 0. Okay. All right. Thus, W minus V is W is CT, so that's CT. V is BS, so this is minus BS. Okay. But this is simultaneously equal to AT minus AS. Right? Thus, using subtraction of these two equations, what do I get? I get that c minus a times t plus a minus b times s is equal to the 0 vector. Okay, so this is just using those vector space axioms here, distributive property in the scalar slot. Okay, and so what does this mean? Here I have this seeming linear independence relation, or sorry, linear dependence relation between t and s, but t and s are in different directions from 0. T and s are linearly independent since they are in different directions from 0. Okay. Thus, when you have a relation like this, all of the weights, all of the scalars actually have to be 0. So c minus a is 0 and a minus b is 0, i.e. c is a and b is a. And so what do I have here? V is as and w is at, which is exactly what I was trying to prove here. Right. There it is. So that's the vector Thales theorem, right? Okay. All right. So that's our vector Thales theorem. One more. So vector Pappus theorem. Now, it is going to make us happy to actually draw a picture in this case. Okay, and so let's draw a picture like this. So this is going to be my vector Pappus configuration. Okay, so let's have okay, that looks pretty good. Let's use a different color for 2 others here. Okay, and then the last 2 going to be dashed lines. So let's slap labels on these. This is the statement of vector Pappus. So this is the 0 vector. Okay, this is W. Okay, here is R. Okay, here is S. Okay, here is V. Here is T. And here is U. Okay, now we're going to fill in a little bit more of this diagram as we go through the proof. So first, let's do the statement. So this is the vector Pappus configuration. This is, if I blew this up a little bit so you could see it, sometimes this is called the Pappus hexagon theorem. So that was also true of the Pappus theorem that you proved as part of your first homework. So vector Pappus theorem, what is this? If R S T U V and W lie alternately on two lines through 0. What do we mean by lie alternately? So R is on one line, then S is on the other line, then T is on the same line, then U is back to the second line, then V is on the first line, and W is on the second line. So I know that that's a little confusing to use that, but it's better than saying, look, here's the Pappus configuration. But this is typically when you're dealing with Pappus theorems, we will say exactly that. We'll say consider the Pappus configuration. Okay, so say they lie alternately on two lines through 0. Okay, with U minus V and S minus R parallel. So that's the two red lines parallel. Okay, and T minus S parallel to V minus W. Okay, that's the two blue lines, the two solid blue lines parallel. Okay. Then the two dashed lines are parallel. So then U minus T is parallel to W minus R. Okay. So there's my situation. Okay. Proof of this. So since U minus V is parallel, I notice that my V's look very similar to my R's, so I'll try to fix that. So since U minus V is parallel to S minus R, again, my R's and V's look very similar. So since U minus V is parallel to S minus R, by definition, U is equal to A S, and V is equal to A R for some A. Okay. Okay, so let's see here. So here is R. Here is V. Okay. So we know that V and R are scalar multiples, but the fact that these red lines are parallel means that the scalar multiples have to agree. So U and S are scalar multiples because they both lie on this line through 0. R and V are both scalar multiples because they lie on the same line through 0. But the fact that we have these two red lines parallel means that the scalar multiples from each of these relationships actually have to be the same. So both of these have to be A. That's what's going on here. And so U is A S and V is A R. Okay. Okay. So I'm filling out my diagram here. Okay. Since T minus S is parallel to V minus W, we have similarly S is equal to BW and T is equal to BV, okay, for some B in R. Okay, so then S can be rewritten as BW. Again, we knew that S is a scalar multiple of W, so that fact just comes from looking at this picture. But the fact that this B is the same scalar in the relationship I'm about to write here, T is BV, again, we knew that T and V are scalar multiples, but it's the fact that it's the same scalar B here for both of these. Okay. All right. Thus, what does this mean? Thus, U is equal to AS, but S itself is BW, so this is ABW. Okay, in fact, I'm going to write that here in my diagram. This is ABW. And T is BV, but V itself is AR, so this is BAR. So again, filling this out, this is BAR. Okay. Thus, U minus T is ABW minus BAR. But AB and BA are the same for real numbers, right? And so this is AB times W minus R, just using my vector space axioms. Thus, U minus T is parallel to W minus R. Which is exactly what I wanted to say, that these two dashed lines are parallel. Okay. Now, this seems like a very straightforward and simple proof once you have this picture and once you just trace through this. This is literally, I'm just using the definition of parallel here. Okay. And just carefully keeping these, but there's keeping track of these. But there's one thing that seems like a very obvious thing, seems like it's a very very simple thing that could be overlooked, which is what is the key thing that uses something other than the definition of being parallel? So this line is definition of parallel in both slots. So it's definition of parallel coming from here and definition of two points as vectors lying on the same line through 0. Again, that's a definition of parallel. So definition of parallel, definition of parallel. This is just rewriting those things, right? This is some basic algebra. This is definition of parallel. So then the only thing that's not just definition of parallel in this vector setting is this thing, where we have made use of the fact that AB and BA are the same. This is a subtle point, but this is a very key fact. So note, subtle point here. This relies on AB being equal to BA. Now, that might seem like a silly thing to point out, okay, because you could say, oh, there's tons of things that rely on commutativity of multiplication of real numbers, but it turns out this is important later. So this is important later. The reason this is important later is that it turns out that the Pappus theorem itself is a fundamental theorem in a setting for geometry that is different from the setting that we've seen. So we're going to talk about projective geometry starting in chapter 5. And in projective geometry, you still have a Pappus theorem. The Pappus theorem is like a fundamental thing in projective geometry. And ultimately, one of our main goals in projective geometry is going to be to develop algebra in projective geometry. And it turns out that in order to get the commutative property arising in algebra from projective geometry, you need the Pappus theorem. And so this Pappus theorem is somehow fundamentally connected to the fact that A times B is equal to B times A. That seems like a really strange thing, but that is actually exactly where this construction of the commutative property is going to come from. And that's where it's going to arise out of when we talk about projective geometry. Okay, so I believe that's enough for this lecture. So in Friday's lecture, we'll pick up here and talk about midpoints and centroids and a little bit of the inner product, what it means about length. And we'll basically from there be tidying up and seeing exactly what benefit we get out of this vector setting when it comes to describing things like rotations and things of that nature, and being able to actually talk about cosine and sine of angles and stuff like this. Okay, so anyway, this is enough for today. So I will see you all on Friday.